So yeah, so where we're at on Friday when we last saw these boxes. So box A was 2.5 kilograms, B was 3.5 kilograms. So your force of gravity on box A is this negative 24.5 newtons. On box B, it's 34.3 newtons. So your net force ends up being 34.3 newtons in a direction that we arbitrarily decided to call positive. You guys know what I mean when I say arbitrarily? Like, it doesn't, there's nothing magic in the fact that I made this positive. We just decided, let's make that way positive because that's the way everything's going to move, right? So are we good up to there? Okay.
Wait.
So, yeah, go ahead.
What did you say the net force was?
9.8 newtons.
Oh, okay.
Good.
I think you said the net force was 34.
Okay, either I misspoke or you misheard me, but yeah, I mean, the gravity over here is 34.3 and net force is 9.8.
Okay.
Are we good? So then, that's the net force on the whole system. So to find the acceleration of the whole system, you've got to use the mass of the whole system. So this 6 kilograms that I've got here is just the combined mass of boxes A and B. 2.5 plus 3.5 gives you 6 kilograms. Cool. So the acceleration of the whole system is 1.63 meters per second squared. Are we good with that? Okay, so question A asks us for the tension in the rope. So I know I mentioned this on Friday. I want to make sure that it's emphasized. That why is it that when I did this setup here, I didn't label the tension force anyway? Why not? Any idea?
Because it's a force in the system, so it doesn't act on the system as a whole.
Perfect. That is perfect. If you didn't hear her, she said because it's a force within the system, it doesn't act on the system as a whole. It's what we call an internal force. All right. What objects make up my system here, you guys? Box A, box B, and our massless unstretchable cord, which is part of the system, right? All that cord is doing is it's just allowing a conduit for box A to act on box B and vice versa. Okay? So it's an internal force. So up until now, the tension hasn't mattered. But question A says, what's the tension in the rope? So here's what we're going to do. The tension is pulling both boxes up, which is a little bit weird, right? Because, I mean, box A is hanging from it and box B is hanging from it, right? The idea is if A wasn't there, B would be falling very quickly, but the tension is slowing down how quickly it's falling, right? And from A's perspective, A is moving up because of that tension force. Follow? Right? Okay. So to find the tension, you got to focus on one box or the other. It doesn't matter which one. So pick the one that you think is easier. In this problem, it's kind of 6 of 1. It doesn't really matter. All right. So let's do box A arbitrarily. So here's box A. Let's see. What are the things we know about box A? Well, we know that the force of gravity on it is negative 24.5 newtons. I know that the mass is 2.5 kilograms. And I know one other important thing.
Acceleration.
Good. I know the acceleration, right? Because it's part of my system. So I know that it's accelerating in a positive direction at 1.63 meters a second squared. And since I know the acceleration, I can find the net force by multiplying the mass by the acceleration. Out of my way. All right, and so that gives you a number that I've written on this piece of paper over here. 4.083 newtons. Follow or no? All right, so now we're done. Our net force is positive 4.083. So the question is, what does the tension have to be? So we're just saying what number plus negative 24.5 equals 4.083, right? So in English, the tension force has to be 4.083 greater than the gravity, right? So just add and you get, what, 28 0.583 newtons. There's your tension force. Cool. Bucks. So yeah. Did I make a mistake?
Sean, I'm just for her.
No, the tension should be positive.
It's positive, so if you were added.
The force of gravity is negative.
Right, but the force of tension would be like magnitude. Because like,
Here, let me write out the math. Is that where, would that help?
if we added 4 to negative 24, we get.
Oh, I gotcha. Yeah, just the magnitude. Just the magnitude. So in equation, so if you're going to be confused by that, maybe I shouldn't be so hand-wavy. Here's what I did. We know, by definition, net force is the total of all of our forces. So for us, that's gravity plus tension, right? Now our net force we know is 4.083. That's got to equal our gravity, which is negative 24.5 plus the tension. And then how do you solve it? You add, right? So that's why your sign switches. Good, you guys? So if the algebra is going to help you, by all means do that. And I think honestly you're less likely to make a mistake if you take time to do that. So it's probably safe. Yeah, Alex.
Was the tension technically G negative before from B?
And I was about to do that. Yes, you're exactly right. So before I go to B, is everybody good with A? All right, now, if we look at box B, may I erase A? I'm not going to go all the way through B, but it's basically the same process. The idea, though, is this. In B, your force of gravity for B is actually positive 34.3 newtons, right? Because of the way we defined our positives and negatives. Make sense? And so that means my tension force is going to be some negative value, right? Because it's pointing in a direction that's working against, the positive, right? So anyway, you go through the same process, and you end up getting the same answer of whatever it was, 28.583, is that what I said? All right. Why am I happy that I get the same answer? What law tells us that it has to be the same? Third law, right? Box A pulls box B with just as much force as B pulls A. So those forces have to be equal. So these problems are cool because there's a built-in safety net. Like when you're done, you can check by going back and doing the calculation for your other object. Or another way you can do it, if this is easier, is assume that's the tension and find the acceleration and make sure you get the same answer. Okay, so there's a couple ways you can do that. All right, did all that make sense?
Yep.
Okay. B and C, I'm going to skip in the interest of time. I'll tell you what, let me do this. Let me give you the answers for them. Oh, that's not what I wanted to do. So B, the answer is 1.48 seconds, and C, the answer is 3.90 meters. Those are just solved using the constant acceleration equations. If I remember right, oh no, I guess one of them you're looking for time. So yeah, they're just the constant acceleration equations. You know the acceleration of the system. For B, you know that box B has to go down 1.8 meters. You're just solving for time. Okay. Part C is the one that I think it's interesting, but I think we're a little tight on time. Keep in mind, if box B is going down 1.8 meters, then box A is going up 1.8 meters, right? So at the instant box B hits the ground, box A is already 3.6 meters up, right? Make sense? But it's moving, right? So box B is going to stop moving down, and then box A is now, you've just like sort of thrown it up into the air, right? And so you're trying to figure out how high it goes. And it turns out it goes up another 30 centimeters for a total of 3.9 meters. Okay? So try it. If there's time later in the week, maybe we'll go over it. But I mean, really, it's just constant acceleration problems. Cool? All right. So, forces vector. I don't know if we need to do this example. Oh no, I guess we do. Let me see. The next example is the same example, but with... Oh no, we haven't done friction yet. So we do. We totally have to do this. Sorry, I'm getting mixed up my honors and my Weirdly, my honors class is after you guys, which is weird. But there's a bunch of stuff we haven't done. We haven't done projectiles, so anyway, it's messing me up. Okay, so here we go. We got a lawnmower. All right, now when you push a lawnmower, you don't push it horizontally, right? Because it's on a handle, so you're pushing down at an angle, right? So we need to find a way to deal with this, all right? And that's kind of what this problem is about, all right? So draw yourself a lawnmower. I drew one for you there, so write down the mass. It's 40 kilograms. Right away, again, remember you guys, you have to get in the habit of mass and force of gravity. Mass and force of gravity. Okay, that's your jumping off point. So my force of gravity here is just going to be negative 392 newtons. Cool. All right, so that's always step one, mass and force of gravity. Step two would be any given forces. So if you read through the problem, it says, assume the wheels are frictionless. Roy pushes the handle with a force of 90 newtons at 50 degrees below the horizontal. So his force is going to come at an angle like this. Okay, so let's go over here and draw that. So here's the force of Roy. The problem tells us that it's 90 newtons and that this angle here is 50 degrees. Well, if you had to hazard a guess, what do you think we're going to do?
Find the x component.
And the y component. Finish the triangle. Find the two components. There's an oops. There's an oops. There's an x component that's pushing the mower forward. That's what's going to make the mower move. Ethan, guys, thank you. Sorry, you're distracting me. There's also a y component that's pushing the mower down, right? Okay. Eventually, we're going to deal with friction. I don't know if you guys remember, but remember, the force of friction depends on the normal force, right? So him pushing down on the mower is going to increase the normal force, which is going to increase your friction if there wasn't. Okay. But again, we're not worrying about that yet. But it's coming down the road. Is that what you're going to say? You sure? Okay. All right. So, does anybody need? You guys don't need me to go through this, do you? All right. So, if you find these, the x component turns out to be 57.9 newtons, and the y component is going to be negative because it's downwards, 68.9 newtons. What, 0.9? Yeah, there. Cool. Question, Ethan?
So what's wrong with putting the vector?
Here, even? For your free body diagram, no. But we're trying to find the acceleration, and we can't find the acceleration without finding these components. So yeah, I'm going to actually make two drawings here, you guys. The drawing that we're going to use the most is the one that I'm going to put here. It's the one that has the components in it. And honestly, I think you guys will, that's sort of like how you're going to solve these problems, is by making the drawings with all the components drawn in. Then at the end, you got to go back and make your free body diagram, which 9 times out of 10 is not that useful. Okay. All right, so let's put our forces in. So we know that there is a force of Roy in the y direction, which is negative 68.9 newtons. There's a force of Roy in the x direction, that's an x, which is 57.9 newtons. Stupid arrow. Move. No, that's not what I wanted to happen. All right. Everybody okay up to there? All right. What other force am I missing? Normal force, right? How much normal force should there be? It's got to be enough to cancel both of these guys, right? Algebraically, it would be normal force minus 39.2 minus 68.9 equals 0, right? Because our vertical forces have to cancel out. Because the mower is not moving down through the ground, and it's not moving up off of the ground, so the up and down forces have to cancel. Okay? So to figure out what it is, it gives you like 461. It's like 460. What is it? Cool, thank you. What were you going to ask, David?
No, I was just saying.
Oh, I got you. Okay. All right, are we good up to there? All right. So, and now we can find our acceleration, right? Acceleration is just going to be net force over mass. So let's see, our net force is, well, you guys tell me, what is it? 57.9. Our mass was 40 kilograms. So divide it and you get 1.45 meters a second squared. The acceleration. Good. Now, technically speaking, like if you want to make like a textbook, you know, on the AP test free body diagram, here's what your free body diagram would look like. Let me free up a little space here. I'm going to just go. Do this. Okay. So here's your free body diagram. Mower. I hate that they use a dot. I don't know why this bothers me so much. I got to just get over it. All right. So there are. There's going to be gravity pulling it down. What is it? 392. There's going to be a force of Roy. So draw on your x-axis. Draw on your force of Roy. Label your angle. And then draw on your normal force. I guess I should have made this force longer, huh? And then the normal force, I'm not going to quite have room for, but normal force is, what do we get? 460.9? Okay, so there's your like, that's your technical free body diagram, which does exactly what Ethan said. But my concern with it, you guys, is that this drawing, just by looking at it, you have no way of knowing that my vertical forces cancel out. Right? The only thing that we can look at this and know for sure is that there's going to be some horizontal net force, because there's clearly nothing canceling out the horizontal component of Roy's force. But by looking at this drawing, I don't know for sure if my vertical forces cancel out. Whereas this drawing up here shows that, right? Yeah, Parson.
I think if we got a diagram like the second one, would we just point if we did it component proportion?
I'm not sure. I will find out if I go to the conference. It's like it's 12. I've got to sum it up for lunch. My guess is yes. I think they want you to do this,
Okay.
which is, you know, whatever. I got to get over it. All right. Are we good? Yeah. What do you got, Matt? The bottom one would be your answer for the free body diagram. And then your acceleration, obviously, is a slope. We good? Problems, questions, concerns, anything? Awesome. All right. I think, what do we have, one more example or two more?
Two.
Oh, inclined planes, and then all three. All right. So we might not get to this today, but let's at least try to get to inclined planes. So, real quick, if I remember right, 5.3a doesn't have inclined planes on it. Anybody look that far ahead? Okay, good, yeah. So we've done everything that you need to do 5.3a. So,
Oh, it wasn't due today?
no, it's due tomorrow.
Whatever.
Sorry. So,
I was telling everyone it was due today.
I guess honest question then, you guys. Do you want to, so here are the choices. We can muscle through, try to do inclined planes real quick now.
Sure.
And then just use tomorrow to go over 5.3a, and then you guys can have some time to work on 5.3b.
Yeah,
Is that what you want to do?
Yes.
All right.
Let's
Okay.
try door number 2.
Door number 2 would be just finishing up these notes tomorrow, and you'd have time now to work on 5.3a.
Still have like.
Let's do it? All right. Okay, so inclined planes. You guys did some of this last night, yes?
Yeah.
All right. So I'm going to assume some level of knowledge. I'm going to go through this. I'm going to say everything, but I'm going to kind of hit it quickly, okay? So here's the deal. Because my box is on an inclined plane, it turns out that most of the forces, let me rewind. Every problem we've done up until now, when we found our components, we've dealt with x components and y components, right? Because our plane has been horizontal, so our motion has been horizontal, right? And the only weird force was like the force on the mower hand, right? But other than that, most of our forces were either horizontal or vertical. All right, but this time that's not going to be true, because check it out. If I'm going to push this thing up or down the ramp, I'm going to push it at a weird angle, right? If there's friction, the friction is either going to go up the ramp or down the ramp. The normal force, point for me, which way does the normal force go? This way, right? So everything's at a weird angle except for gravity, right? So what we're going to do is, instead of using an x and y plane, we're going to use what I call a parallel plane and a perpendicular plane. Rewind, I said that wrong. Instead of using an x and a y axis, we're going to use a parallel axis and a perpendicular axis. All right? So ordinarily, we'd have x-axis, y-axis, right? That's not going to help us a ton because our motion isn't going to be along either of those. So let's rotate our axis system so that the motion is along one of the two axes. So I'm going to, and I'm going to call this guy the parallel axis, and I'm going to call this one the perpendicular axis. Okay? And what that buys us is all of the forces, pretty much all of the forces are going to be along one of those two axes. And it simplifies things. Okay? So, this I am going to call the perpendicular axis. This I am going to call the parallel axis. Geometry symbol for perpendicular, geometry symbol for parallel. Cool? This notation is not in your textbook. They're very hand-wavy about this. And I have always found this to be the easiest way to solve these problems. All right, so are we good up to here? All right, so in this problem, because there's no friction, there are only two forces. So what are the two forces? Gravity and normal force, right? So gravity we can sort of find. It says it's an unknown mass. Oh, yuck. So,
Ours is 4 kilograms.
oh, shoot. Yeah, I printed that out. Cross it out. We know the mass. Ha ha ha. You don't need it. It's going to cancel out. Oh. Right, my bad. Okay, so anyway. So let's pretend it's unknown mass. If you really want, you can do it with 40 kilograms, but you don't need it. All right, so gravity is going to pull this thing down, right? Force of gravity. So if we knew the mass, it would just be m times the acceleration of gravity, right? Or you could write mg if you want. Just remember that whatever it is, it's going to be negative, right? All right, and then we're going to have a normal force, which you guys already told me was going to be this way. Cool? All right. So, the problem is, much in the same way that the lawnmower handle wasn't along either of our axes. Oops, I just went past it. Yeah, you can't really see it. This lawnmower handle wasn't along either of the axes, so we had to find the x and y components, right? Now we got kind of the same idea. Our gravity isn't along either of our axes. So instead of finding the x and y components, we're going to find the parallel and perpendicular components, exactly. All right, so we're going to have one component that goes this way, and one component that goes this way. So this guy I'm going to call FG perpendicular, and this guy down here I'm going to call FG parallel. My right angle is here. Now, before you draw it, please notice, I think most of you know this, but I just want to make sure that everybody gets it. This sort of bottom side of the triangle is not horizontal. It's at an angle parallel to the ramp. Make sense? Everybody good? All right, now, it turns out you can do some kind of simple geometry. So this angle here is 30 degrees, right? That means that this angle here is also 30 degrees, right? Because the blue dotted line and the surface of the ramp are parallel, right? Okay? Well, that means that this little angle in here is 60 degrees, which then means that this guy in here is 30 degrees again, right? Say that again.
I thought that you wrote the 3 times 30, but what are you drawing between the parallel and this?
The blue dotted line and the horizontal.
Okay, but why does it 3 degrees in between the 2 parallel?
Oh, no, I'm sorry. I see where you're confused. So 30 degrees, 30 degrees. Cool. Yeah, sorry, that wasn't clear in my first drawing. All right, everybody good? So long story short, this angle here is always going to be the same as this angle here. Always. Yes. Yeah, I see that for sure. He's saying that if you imagine, well, it's not really even. because this side is your hypotenuse. So if you flip it, then it's going the wrong way.
Flipping around and trying to.
I gotcha. I see what you're saying, but yeah. Yeah. Okay. Question or comment over here somewhere? Okay, cool. So, so based on this little triangle, you can pretty easily figure out that, oh, well, this means the FG perpendicular has got to be my hypotenuse, which is FG, times, well, this is my adjacent side. So I'm going to use cosine to get the perpendicular one. And then your FG parallel, I'm going to write it over here, you use the sine to get. This is always counterintuitive. It's backwards from the way that I always want it to be. Because I always associate the parallel with the x-axis, which makes me think cosine, but it's not. The parallel one uses sine. So I remember the first time I did this, I didn't look at the equations carefully, and I kept switching them. So just make sure you're conscious of that. All right, so are we good? All right, so there's a blank page. Cool. All right, so here's our drawing. So here's the box, or here's the ramp, here's the box. So what I'm going to do is, instead of drawing in my force of gravity, I'm going to draw in my FG perpendicular and my FG parallel. So those two forces are replacing my one force of gravity. If you use vector addition and add these guys, it gives you that force of gravity that we started with. Cool? And then there's a normal force. Follow? All right, so this is mass M. So remember, Fg was just mg or mag, however you want to do that. So that means that this guy is going to be Fg times, which one did we say perpendicular was? Sine, right? So this is m ag sine of theta. And this one over here is going to be m ag cosine of theta. Okay, Alex, what's wrong? Oh, no, they're wrong. You guys know. Whoever said sine was...
Yeah.
Sorry.
Wow.
I was blindly agreeing.
I just give you side.
I fooled myself. So perpendicular should be cosine, and this one should be sine. Sorry. That's embarrassing after I just spent all that time saying, make sure you don't mix them up. And then I did. All right. So, are we good? All right. So, point for me. What direction is the acceleration going to be in? That means it's also in the direction of the net force, right? So what has to be true about these guys? They have to cancel each other out, right? My perpendicular components, as long as the box doesn't leave the ramp, my perpendicular forces have to cancel each other out. So this is going to be mag cosine theta. Cool? All right, so my net force then is mag sine theta, right? And so my acceleration is net force over mass. Aha. What happens? Masses cancel out. And so the acceleration is ag times the sine of theta, which should look familiar. Why? That's the diluted gravity equation that we used when we did the lab, right? So that's where that comes from. That's why I didn't want you to know the mass. Now, obviously, if you knew the mass, you could certainly plug it in, and that simplifies things a little bit. But cool? All right, questions? How are we doing? Good? It's a lot, but most of this stuff is review for you guys, right? You guys have all seen this stuff, yes? Okay, cool. All right, so last example, we got 15 minutes. See, I think we can get through it. Fingers crossed. So this one has a whole bunch of stuff going on, all right? So did I give you guys a drawing? Shoot, I meant to put one in. That's okay. All right, so a 25 kilogram box is placed on a frictionless plane inclined at 40 degrees. Plane inclined at 40 degrees. This time I gave you the mass of the box, 25 kilograms. It is connected to a massless, unstretchable string which runs over a pulley at the top of a ramp, at the top of the ramp. So here's your pulley, string, string. Dangling from the other end of the rope. Oh, my string turned into a rope. Sorry, I hope that's not confusing. 30 kilograms. If the 25 kilogram mass is pulled, as shown, I didn't put it in the drawing, I apologize, with a force of 100 newtons at 20 degrees above the horizontal. All right, so there's no way from the text here to know which way. I intended for the force to be this way. I'm sorry that I didn't put that drawing in. So the force is, what do we say, 100 newtons? At, what did we say, 20 degrees above the horizontal? All right. So we got to find the acceleration of the system as well. All right. Are we good? Okay. So sorry, I'm just thinking about the best way to go about this. All right. So again, remember when you're doing one of these things where there's sort of more than one mass when you've got a system, the first thing you want to do is sort of look at the system as a whole. Okay? So there are really only well, I guess there are three directions this thing could go. We will quickly find out that this 100 newtons here is not enough to lift the box off of the ramp. And you can do that math real quick. Look, gravity is going to be, almost 250, right? So there's no way this 100 newtons would lift it, right? So again, there are two possible ways that the object can accelerate. It can either go, maybe the 30 grams wins and it goes this way. Sorry, 30 kilograms. Or maybe the 25 kilograms wins and it goes this way. We don't know. But those are sort of our two possibilities, right? So the first thing I want to do is I want to look at the system and ask myself, what are the forces that contribute to the motion of the system either this way or this way? Follow?
Yeah.
All right, so we're going to draw that sort of nebulous system blob. No, that's the worst system blob ever. Well, whatever, we'll deal with it. It's fine. Oh no! All right, so name some forces that are going to affect the motion of the system as a whole. Gravity, be more specific. The gravity on the 30 kilograms is going to be 1. That's going to be over here. So force of gravity over here is going to be, what, 294? I'm not going to assign it positive or negative yet. I'm going to wait and see who's winning. All right? And then I'm going to make whatever's winning my positive direction. Make sense? All right. So that's that. Anything else sort of stemming from the 30 kilograms? Do I need to worry about the rope? No, it's in the system. All right. Let's see. Over here, there's going to be gravity. But which part of gravity do I care about? Which part is going to contribute to the motion this way or this way? The parallel. Do you guys see why or no? Okay. So let's see. I got to figure out what that is. So that's going to be. I should probably label my boxes, right? So call this guy A. Call this guy B. So everything over here is A, and this is B. Okay. So somewhere off to the side, we need to do some quick calculations. So let me free up a little space. Whoa. There's more than I wanted to free up. Whatever. So the force of gravity on A is 25 times 9.8, right? So that's 245 newtons. Negative, I guess, technically, right? So the force of gravity A parallel is going to be 245 times the sine of 40 degrees, right? Figure that out. It gives you 157.98. Is that what it says?
48.
48. Thank you. So 157.483 newtons. Good. Now, anything else? That applied force, right? So before I do that, was that a question, Patrick?
Will you give us the other one too? The other side of the triangle?
Oh, sure. Yeah, I wasn't going to calculate it till later, but yeah, we can do it real quick, I guess, while we're at it. I don't remember. If you figured out, though, that perpendicular component turns out to be 187.68. 68, 1 here. Again, I'm keeping insignificant digits here. What's that? We're going to need it later. Oh, actually, no, it doesn't affect this problem. But next chapter, we're going to deal with friction. And you need to know that perpendicular component, find your normal force, which will affect the friction. So I would get in the habit of finding it. All right, everybody good?
Yeah.
All right, so now we got to deal with this this thing, right? We've got this 20 newtons, right? So, sorry, 100 newtons. Sorry, I said 20. It's 20 degrees. All right, so let's see if we can figure this out. So here's our box. We've got this force that's kind of going this way at an angle of, or with a force of 100 newtons. And I know this angle here is, what is it, 20 degrees? Wait, you got to add the 40, exactly. So, oh, Jesus, this is terrible. So that's 20 degrees off the horizontal, but this is 40 degrees off the horizontal. So this whole angle here ends up being 60 degrees. Does that make sense?
Yeah.
Alex, you good or no? Here, let me do this. Let me make a better drawing.
Isn't it
So here's the ramp.
60?
So here's 40 degrees, right?
Yeah.
Here's the 100 newtons. 20 degrees, right?
So isn't it just like to the top of the box, it's 60?
Yeah. Yeah, because the top of the box is parallel to the ramp.
Yeah.
Yeah, that works if that. Yeah, I'm cool with that. All right, so if you kind of extend this, you can see. So this is 40, this is 20, so you've got a total of 60 degrees, right? Cool? Cool. Right. So we've got that force of Roy. We need to figure out the parallel component and the perpendicular component. Here's my 60 degrees, right? Oh man, parallel component doesn't look parallel. Why am I having such a tough time making this drawing? There we go. A little better. You guys see that or no? All right, now, the 100 newtons is the hypotenuse. Which trig function will give me the parallel component, sine or cosine? Cosine, right? Because it's the adjacent side of this triangle, right? You okay, Missy? Saw the agony. Are we good? All right, so our F parallel is going to be F times the cosine of 60 degrees, and our F perpendicular is going to be F times the sine of 60 degrees. Notice, these are the parallel and perpendicular components of the applied force, not gravity, right? So that's why we're not tied to the sine cosine conventions that I showed you a minute ago. Clear?
Yeah.
Okay, so 100 times the cosine of 60 gives you, let's see, so this one's going to give you 50 newtons. And then the parallel one, we don't really need to solve it. Or sorry, the perpendicular one, we don't need to solve it. But it turns out to be like 86.6 newtons.
And speak with you, especially in light of the recent outcome of our presidential election last night. I'm not a professional speech writer. I don't have someone who writes speeches for me. I come on this PA and I speak to you from the heart. As your principal, I witnessed a divided school, much like we witnessed a divided country in the outcome of our election. I've seen students crying this morning because they're mourning the loss of the election last night. And I've also seen students in jubilation for the win. And that is representative not only of our school and our community, but of our greater nation. This is an opportunity truly for us to come together with civility, work with one another, and move our country forward. Then we need to prepare ourselves to engage in difficult conversations around many different topics: racism, civil rights, immigration, and so forth, that this election has raised. Your lives, your experiences, your culture, your background that represent our school and the greater community can lead to some high-stakes conversations that are uncomfortable at times. Trust me, I know. But I